Hello, my name is Walter Unglaub, and this is the kinematics of angles in physics. The kinematics of angles in physics is very similar to the kinematics of linear motion and position in physics and introductory mechanics. If one typically considers circular motion, we can write down a relationship between the angle and distances if we examine the radius of the circular motion and the arc length. So this angle, theta, is related to the radius and the arc length in the following form. The arc length is going to be equal to the radius times this angle, or change in angle. The angle is measured typically in radians, where 1 radian, or rad for short, is equal to 360 degrees divided by 2 pi. And that's going to approximately be equal to 57.3 degrees. So you can use this conversion, this equivalence between degrees and radians if you so desired. Now, because of this relation, we know that the angle is then viewed as a ratio of the arc length divided by the radius. So as this arc length increases, so too will the angle. So now let's go over the kinematics. We have an angle which we're going to treat as a type of position in circular motion. And if we take the time derivative of that angle, we end up with the angular velocity, which is denoted with the Greek letter omega, the lowercase one. So we can denote that as theta dot. If we take the time derivative again, then like in linear motion, we develop the idea of an angular acceleration, where alpha is typically used. So alpha is going to be equal to the second derivative of theta with respect to time, or just theta double dot. Now if we start with the angular acceleration, then we can derive all of the kinematic equations for the angle. So the final angular velocity is going to be equal to the time integral of the angular acceleration. So if we assume that the angular acceleration is constant, then we get out alpha t plus omega naught, which is the initial angular velocity. If we integrate this once more with respect to time, we're working backwards here, then we're going to develop a kinematic expression for the angle theta, the position, so to speak, in the circular motion. So theta final is going to be equal to the integral of omega, which is a function of time, with respect to time, and we get out 1/2 alpha t squared plus omega naught t plus the integration constant, which is interpreted as the initial condition or the initial angle. So therefore we get theta final is equal to theta initial, or theta naught, plus omega naught t, plus alpha over 2 times t squared. And this is our kinematic equation or expression for the angle under the consideration of circular motion. My name is Walter Unglaub, and this is the kinematics of angles in physics.